Boom. Hello and welcome back to Calculus 3, section 11.4, cross product. We're going to continue learning about ways to multiply vectors. So previous section we talked about the dot product. Time before that we talked about scalar product of the vector, which just made the vectors longer or shorter. And now we have a new way to multiply vectors. And since in some sense the dot product, should I say, celebrated or acknowledged the same components of the way they combine of two vectors, the dot product is going to be concerned with their differences. So they kind of together cover everything. So the cross product is different in a sense that it's not possible to do dot product in any number of dimensions. There are just some dimensions where the cross product can be worked out, and if you are interested in cross products beyond 3D, the next stop will be 7D. You can go on and look up all of the dimensions that allow for a cross product. So we are immediately going to kick out all of the 2D vectors from the realm of cross products, because cross product cannot live in a 2D space, and we are going to see soon why. Now the cross product is going to be denoted as vector u cross vector v, and as I said, this is so I'll just say 3D only. It's not only, it's 3D and then other dimensions, but since in Calc 3 we are only concerned with 2D and 3D, all right, fine, between those two it's only for 3D. So we have the cross product between, let's call them ux, uy, uz, crossed with vx, vy, and vz. So u cross v is going to be the determinant of the 3x3 matrix, where components I, j, k, which are the unit vectors, go on the first. Ux, uy, uz occupy the second row, and vx, vy, and vz will be on the third row. Now the way we compute the determinant is, all right, so maybe you should just observe this and you can write it later, because it's a pattern, and it looks really complicated, but it's really cheap. So just stare at the screen rather than your notes and then write it later. So here what I'm going to do. I'm going to start with I. And if I'm starting with I, that's going to kill the row and the column. And what you are left with is the determinant of the matrix that you see, which is 2 by 2. So that's going to be I times uy, uz, vy, vz. And then we have minus j, and that's a killer right there, that negative sign. So you have to remember that one. Now there goes the same deal. Kill the row and column, and the determinant of the matrix that you need to work with is ux, uz, vx, vz. And finally we have plus k, determinant of the matrix. So now we're killing k, row and column, and the matrix that stays behind is ux, uy, vx, vy. And now we need to compute each one of these. Now 2 by 2 determinants should not be that much of an issue. We have If you haven't seen the before, this is the fastest way to remember that one. So you will multiply uy by vz, and then you will subtract vy uz. Now, if you are carefully observing this symbol, oh, come on. If you are carefully observing this symbol, you see that there is like a multiplication x in the middle. So it's u times vz. This is flat, so it's a minus sign. And then another multiplication going this way. So if that helps, use that. So uy vz minus vy uz minus j ux vz minus vx uz plus k ux vy minus vx uy. You ever had larger formula? So next time someone tells you, what do you know? Write this out.
So why is the J negative?
The way I'm going to answer the question, why is J negative, I'm going to say linear algebra. Okay? That's the best answer that I can provide at 40 minutes before class, or the whole section ahead of us. So the signs will alternate. You have I, negative j, positive k, and you will have the 3 2x2 matrices. You're killing the row and column as you go from one vector to another. By the way, the pattern of plus minus continues throughout the higher dimensions. So if you have a 4x4 determinant, I minus j plus k minus l. So you can look that up if you're interested. Now, your cross product, as you can see, deals with differences of all of these that are not the same. Remember the dot product, ux vx, uy vy, w, right, x, vx, they're always the same, and then you're adding them. Now for the cross product, yz, yz, xz, xz, xy, xy, you see there's never xx, yy, and so on. So it kind of fills that gap of what the dot product left. So now, going through this, the first order of business is for you to compute one of these puppies. And then we're going to start with concepts and things. So 2, 1, 3. And v is equal to negative 2, 1, and 0. So let's have it quick. So ijk should have the hats, the unit vectors. I mean, you can put the arrow on them too, but hats are the proper notation for unit vectors. So we all have negative 364? Negative 6?
No, it would still be positive for that.
Because negative and negative is positive. You have a negative j, but you also have 2 times 0 is 0, right?
Yeah.
Oh yeah, there's a minus and a minus and a minus. Yeah. That details. There are 3 minus signs at work. There is a minus in a formula when you subtract these guys. There is a minus 2, which gave you minus 6, and there is a minus on j. So 3 minus signs is a negative 6 in the middle. Yep. Good. Now, I want you to compute v cross u. While still young, let's go. So now find the cross product of v cross u.
So I'm doing.
I did all of this.
I'm not understanding it. What do I do first? So, I just don't understand it. It's gibberish here. I'm not getting. So you do U.
Y.
UY.
Which one is the
this?
No, that's yours.
UY.
Mm-hmm.
Times. I don't even know what this means.
That's the way you write this one out.
Right. This whole thing goes like this. UY times VZ.
Mm-hmm.
VZ is this.
Mm-hmm. 0.
0.
So 1 times 0.
1 times 0 minus VY, which is this. Which one? This one?
Mm-hmm.
Why not this one?
That's U. That's a V.
Oh, this is V.
Mm-hmm.
Oh, these are U's up here. These
U,
are V's.
V.
Alright.
That's the key. That's the key.
That's the key. Alright.
IJK, U's, V.
Okay. Alright. I'll just look at it.
So 1 times 0 is 0.
0.
Minus 1 times 3 is negative 3. Boom, negative 3, 5.
Okay. Yeah.
It's a little convoluted, but take. So do we have the same numbers with opposite signs? We better. because the rule says that the cross product is not commutative, but the cross product, if you swap the order, just picks up the negative in front. We'll explain that also in the physical realm very soon. I have another definition for the cross product. Which says that the magnitude of u cross v is equal to magnitude of u times magnitude of v times sine theta. Hey, isn't that a formula that is awfully similar to your dot product, except you have a sign now? And another feature over here is that you actually have the absolute value, which is the magnitude of u cross v. Well, first off, what did we find when we did the definition up there? We found that our answer is a vector, right? So I need to state that here in blood. Dot product gives scalar answer. Cross product gives a vector. So, and it's not any kind of 3D cross product gives us a 3D vector. So, having these magnitude absolute values on the left hand side makes a lot of sense if you want to dimensionally compare these things. On the right you have magnitude of v, which is a number, magnitude of u, which is a number, and the sine of theta, which is a number. So multiply those three numbers, you get a number. You can't have a cross product which is a vector equal a number, but you can have a magnitude of the cross product. So dimensionally these formulas have to make sense. Magnitude on this side on the vector. So cross product is going to give us another vector. So another 3D vector. The magnitude of that 3D vector is the same as what you have on this side. So now there is a formula for cosine theta, there is a formula for sine theta, and they are right, one for dot and one for cross product. Great. The next question is well, properties. Let's get that out of the way. Properties of cross product. Number one, it's not commutative, but it's so damn close to being commutative, so we just have that minus sign there. So u cross v is negative v cross u. And we've seen that from the example we just did. Clearly that's not a proof. The proof is when you work out the matrix on 2 pages, right? And so, and then we have the associative property. And then we have 2 distributive properties. the cross product is this x. It looks like x, but it's cross. Right? Do we really need rule 3 and rule 4 for distributive property? Can we just by just having one somehow?
I mean, with the first rule, like, we don't have to do it, so we can't do it.
Very good. Yep. We don't have commutative rule. So these things are not commutative. Good. Finally, we get to the point to talk about what this thing actually does. So, the dot product was connected to that projection. And we multiplied x components and y components and added them all together to see how much stuff goes in the same direction. Now, what would cross product produce? Well, first off, from the formula, we clearly see that it produces another 3D vector, right? But it produces really specific 3D vector. Yes? Very good. So what it produces, if these two vectors are the input vectors u and v, the cross product is 90 degrees. It's orthogonal to the other two, to both of them. It's 90 degrees to both of them. So, right now I need you to think of the 3D coordinate system with x, y, and z axis, and place at the origin in your mind's eye, place at the origin 3 unit vectors, I, j, k, right? So you have vector I, which is a unit vector, 1, 0, 0. That's on x-axis. Then you have a j vector, 0, 1, 0, on y-axis. And you have k unit vector, 0, 0, 1, on the z-axis. So all of those vectors are mutually 90 degrees to each other, right? Now, here's the cool exercise that you should try, and it's a very quick one. Take the cross product of any of those, any combination. You will always get the other ones. Now the third one. So I cross j has to give, right? Now you are going to run into issue with the minus sign. Well, that just means whether you multiply k with I or I with k, right? So you have to be careful about that. So essentially, what's happening here? I have two vectors. That one's lost. All right, so I have two vectors. Oh, God, I need a blue one. Stop. Enough exercise for one day. So here are the two vectors, any two vectors in space. When you cross these two vectors with a cross product, you are going to get a vector that it's 90 degrees to the blue and 90 degrees to the black. Now, any way you rotate this in space, it will always orient itself that, let's say over here, black cross blue gives you green. If black cross blue is green, then blue cross black is negative green. Do you see that there is a positive green and a negative green? That is going to depend whether you have a black cross blue or blue cross black. You will have two vectors. So now, further digging into the components, the two vectors are all you need to describe a plane. You can't use a single vector to describe a plane because, as you can see, it's wobbly, right? It's enough to have 2 points in space and stretch a line between those 2 points. You can't do it with 1 point because, as you can see, right, it's wobbly. You put 2 points in place, and that's why your slope equation, right, in algebra, y2 minus y1 has, right, 2 points to it. To have plane, you have to have 3 points, because 3 points is the minimum requirement for the plane not to be wobbly, right? So those are the bar stools have 3, right? Some of them, and then it's funny eventually. So I see some of you can relate because they're smiling. So what are those 3 points? Well, if you call this one terminal, the initial point, you can set your black vector this way, and you can set your blue vector that way, right? So it's definitely 2 vectors are enough to get you a plane. So 2 vectors would describe a plane. So now you have 2 vectors which describe a plane which sits right through those 2 vectors, and that plane is 100% determined by the 2 vectors, i.e. 3 points. Great. We got to the point where we understand that 2 vectors that you are crossing are actually in the plane. The cross product is going to give you the vector that is perpendicular to the plane this way or that way, depending which way you crossed it. Again, blue cross black or black cross blue. So now, and we had the example when we swapped them and we got those negative signs, plus is the property number 1. So these are all the concepts that go together, and you have to keep in mind that the cross product produces orthogonal vector. That is going to be a key point for us moving forward, for many concepts coming along the way. And another one is the angle for the dot product, right? That's another key point where you you dot 2 vectors into a 0 if it's 90 degrees. So this 90 degrees plays a role, and guys, you have to understand the main driving factor of Calculus 1 was tangent line. That was the concept for Calc 1, tangent line. You used to measure the change. That was the derivative, right? The tangent line. So the slope of the tangent line came from the derivative. When we hop into Calc 3 now, your main object you're dealing with is not longer a line, but it's a plane. And this business is going to give us a tangent plane. And the tangent plane is going to be described to the green vector. All right? So the green vector is not just one thing that we mentioned in 11.4, you go on. Hell no. One of the most important concepts of Calc 3 are going to be tangent planes, because they will show the change in a surface. Right? What do I mean surface? Well, you can't ski uphill. All right? And that has some kind of a 3D slope with my air quotation marks, and that's detected through the tangent plane at that point, and tangent plane is this green vector which came from the cross product of 2 vectors that were in the tangent plane. So all of these things together, make a good soup for us to work with. And now we're going to just see those things. Now again, observing the corner of the classroom as your XYZ coordinate system, you have I, J, K components, and please note that I and J, right? So where's my I class? I know it. I have to worry about everything. So if this is the x-axis and that's the y-axis and that's the z-axis, you see that I and j components create the xy plane, and then the z is perpendicular. And you have your x component and your k components, so j and k create this surface here, and then there's your y this way. It's always perpendicular to it, right? So all of those things work together, and you get that stuff with a perpendicular orthogonal, right, in the 3D. Now they give you as a theorem, which I wept when I saw it, because if you can't come up with that, I mean, like, just don't be here. But anyway, what else? So the way to compute it, you did this, and
how does the magnitude relate to the cross product?
well, that was the formula that, in this definition. So the magnitude of the cross product is given by the magnitude of the each one times sine the angle between them. So you can use either the dot product or the cross product to figure out the. I did not solve this for theta, but it's inverse sine of magnitude of the cross divided by the multiplication of the magnitudes. And that gives it. Now, I talked about the cross product. I told you that if you cross so black U with the blue V, you are going to get a green W. So I'm going to say U cross V equals K, and then V cross U equals negative K. Sorry, not K, W. So it matters, the order matters, right? So that's that part. We talked about that. Try crossing I cross J to get something, and then J cross I to create something where you know that I is vector 1, 0, 0. And I'll put 3 dots because you know J and K are 0, 1, 0 and 0, 0, 1. So that's that part. Again, 2 vectors create a plane, but that's just the intro to the much bigger lecture on it next time. And application. And then I guess you want to go home. I don't know. I can stay. No takers? So without a doubt, the cross product, if I have to pick one thing, application, so number one out, without a doubt, is tangent planes. Done later. So that's without a doubt, right? Getting what we call a normal vector and then using it to create a tangent plane and so on. So that's that. But then there are other things that we can do with a cross product. And again, statics, guys. Woohoo! Where are you? So, and physics, right? So you have these concepts of doing something in a plane but the result moving perpendicular from what you are doing. For instance, we're all going to observe now Muhammad leaving the room. He is going to push the door, right? There we go. And those doors were on hinges over there, right? So the interesting thing there is that there are forces at work that you can consider. So that's one of the things. We can also think about the screwdriver or the angled wrench, right? Which brings in the circular force called the torque. And as you in plane, right, either turn the screwdriver or the wrench, which all happens in the plane, the force goes perpendicular to that plane. So there is that part of as well. So let's take a look at a few of those now. Also, magnetic and electric fields. Just talked to one of my past students. That was yesterday, who was telling me that in his fish tanks there was voltage inducted because of the cable management that he didn't do properly. He's big into tanks, has multiple saltwater tanks with corals and everything else. It's almost like an aquarium in his house, how many he has. So the wiring, the way it was out for all the lights and heaters and everything else, the pumps, right, was actually inducting voltage into the water. So there's a lot about magnetic fields and electric fields and interaction of those, where one turns into another through the process called induction. So all of those are here. So let's first think about this. So the force, right, the torque is going to be the force times the radius where the force is applied. So if you think about it, the wrench, ratchet or whatever, right? This is, by the way, perfect. It's just your eyes are terrible. So if I want to find this circular force, it's going to be the radius times the linear force across with the linear force applied. I'm not sure if they have this example in the book still, or if this book has it at all. I don't see it. Oh, they do. So what's happening here, guys, is that, and the reason why I asked you to observe Muhammad leaving the classroom earlier is because this R is extremely important in this formula. If you apply force, linear force over here, you're expecting the torque this way, because you have a fixed point where you are connecting with the screw that you're working on, the bolt, whatever, right? So observe that you could apply the force here. The issue is that if you apply force on the top, right close to the screw, the radius to where the bolt is very small, which means that this being very small, since it's right? It's proportional to the torque, you're not going to have a lot of torque. The longer the handle, the easier. So now, as you're leaving the classroom, it's common sense that all of you are going to push at the door as far to the right, in this case, as possible. You want to push the furthest away from the hinges. And you know how silly you look every time you're at the store and you're not paying attention. You want to go out, the door looks the same, there's no handle, right? And you push on the other side, close to the hinges. Does the door open? No, right? If you push at the hinge, it can't open because you are creating zero force, zero torque. Remember, your R in that case is 0 because hinges are fixed point, right? And you measure the radius from the hinge or from that fixed point, whether it's a bolt or a hinge, right? And if you push there, the door is not going to open, right? So over here, pushing it, not a problem, right? The door opens. The reason is, if you look from the top of the door, the radius, R, is from the hinges all the way to the end. So if I'm pushing here, it's not an issue. Anyone can open the door. But if you push at the hinge over here, it won't work, right? If you push here, well, I'm fairly strong, but if you try it, you won't be able to do it. Try it later. So that's the deal. So it's radius times the force, and it's the cross product of these two. So there's your application. I'm going to erase this and draw radius. So this is your R from there to there. Now, all I need to do is to draw another view for all of you statics people and have the door over here. Maybe I can open the door. There we go. Open the door, and there's the wall. Continue. So this is the wall. This is the door. And this is the wall, right? So now you will be pushing with your force there. And again, only the perpendicular component. The perpendicular component is the one that does the pushing. It's not going to be, you can push at the angle, but it's harder, right? If I push, so then you will have to actually use the 2D projection, right? If you push this way, it's not going to be as easy as if you push 90 degrees. So it's a 90-degree force, and you would use the projection thingy to determine the F to do that. So you guys have fun with that. Times the radius, which is the length of the door, right? What? I mean, we have to have these to accommodate everyone to pass through them, right? So there you go. That's the radius, so that will be like, what, 4 feet, let's say, or 3 feet, whatever it is. And then you have the torque. The torque will be going around the fixed point, which are the hinges. So again, this is the top view. This is for those of you who are not versed in technical drawings. It's the top view of the door and the wall. And there you have it. So now, I mean, if I give you that the force is 20 newtons and the door is 4 feet, right? You just plug those in a cross product and you're done. So it's fairly simple. The amount of torque is going to be the magnitude of the vector that you get, right? And those kind of things. Man, I don't know. I don't have any kind of grand finale thing or dropping the mic because I don't have the mic, so I'm just done. That's it. I'll see you Wednesday.